Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed how we can derive the maximum peak overshoot of this in this response of second order system. So in this lecture, we are learning how we can derive the settling time expression. So let us start our session. So if we observe the second order response of this system, second order system, then we are having this kind of graph over here. So this is the steady state value we gave to this system, and this system is approaching the steady state value by having decaying oscillations with respect to time, and it is reaching, these oscillations are died at t equal to infinite. And this, if these oscillations are within this 2% tolerant band, the first time at which these oscillations are reached at 2% tolerant band, that time from the starting time it is called as settling time. So how we can derive this settling time? So let us see. So 2% means 0.02 amplitude. So the expression which is varying with respect to time, which is oscillating about this one steady state value of 1, it should reach the value of 1.02 or minus 0.98, because it is plus or minus 2%. So it can be more than that, it can be less than that. So let us assume that this response over here is reaching its maximum value and it is exponentially decreasing like this, and it is reaching the 2% band at this position over here. So this time over here is what we call it as the settling time. So let us derive the settling time. So at this settling time, t equal to ts, we have this c of ts value as 1.02. So if we equate that, then uh, we can have, so this one will be possible only. So this is something which is subtracted over here from 1, and this value, in order to be greater than 1, we need this value as negative value. So this exponential cannot be negative, so we can equate this sine of omega dtp plus theta as -1, negative value. Why? Because it is the maximum value we need to take over here. So sine theta maximum value is 1, and when as this expression cannot go beyond 1, so we need to take -1 over here. So we have 1 plus exponential of minus del omega n. This is, sorry, I'm sorry, this is ts over here. This is ts over here. So ts by root of 1 minus delta square equal to 1.02. So if we subtract this thing over here, we have 0.02, which is the 2%, which is equal to exponential of minus del omega and ts over here, and root of 1 minus delta square. So if we equate this by, if we solve this by applying logarithmic on both sides, then if we apply log on this side, if we move this to this side, then we have 0.02 into square root of 1 minus delta square. So if we apply logarithmic on both sides, then we have del of omega n into ts is equal to logarithmic of 0.02 into square root of 1 minus delta square. And if we find out like that, then we have the ts as for 5% tolerance band. Like if we This is for 2% tolerance band. That is 2% of either increase or decrease with respect to 2%. But if we take 5%, that is 0.05, then we have the settling time as 3 by delta omega n. So 1 by delta omega n, we can write it as tau. And for 2% tolerance band, if we solve that logarithmic value and everything, then we are left with this settling time is equal to 4 by delta omega n. So this 1 by delta omega n, we can call it as the time constant. So this is how we can derive the settling time for this second order system for different tolerance bands. So that's all for today, guys. Thank you for watching this amazing video.